Our third presenter is Ivan Laso from Florida DOT. He's the Steel Materials Administrator for Florida DOT.
Good afternoon, everybody. Before I start, I would like to thank TSP2 for allowing us to share some of our work with you all, and hope that you will find it interesting. I would also like to take the opportunity to thank my co-author here on this presentation with Mr. James Jacobson and Mr. Steve Womble from our Bridge Structures Maintenance Office, which they are the ones actually responsible for the bridge. From our group, we provide consultation, but they are the ones that have the responsibility for maintaining the bridge, and more than anything else, to secure the funding for all this work. Well, before we start, I would like to start with a little background of the bridge. The Sunshine Skyway Bridge is located in the west central coast of Florida, just south of Tampa. It connects the cities of St. Petersburg and Bradenton across the entrance to the Tampa Bay. There used to be another bridge at this location, but in May 1980, a ship impacted the old bridge, which made the main span collapse in one of them. It was a very unfortunate incident for Florida. But then back in 1987, we were able to replace the old bridge with a new state-of-the-art bridge for the time. And the DOT wanted to make sure that we improve the safety features on the bridge, just to make sure that what had previously happened with the old bridge would not happen to this one. So, in summary, the bridge is considered the flag bridge for the state, and it really received significant attention. This is the bridge profile. This particular bridge, it is a very complex structure. It have actually three different types of bridge structures. The bridge itself have three different sections, basically. We have at the end the low-level approaches. We call it the trestle spans because they are typical footer and columns with ashto beams supporting the deck. Then we have what we call the high-level approach spans. Those are post-tension columns on a segmental section on this bridge. Then we have what we call the main spans. Again, these are post-tension columns with the two center piers being holding the state towers. The center span, as you can see, it is a cable stay bridge. It holds the bridges. And down in this area, we have some massive footings to support those towers and the load. So basically, like I said, it's maintenance of this bridge requires detailed attention, a lot of work, and a lot of overseeing because of the amount of so many different structural components that our maintenance group have to deal with. In order to do that, what the bridge office in charge of the bridge decided some years ago, they established what we call the Bridge Preservation, the Skyway Bridge Preservation Committee. It was established in 1999, basically to assist on the maintenance of the bridge. The goal of this particular team is to look ahead on the service life of the structure and identify all those situations which could compromise the service life of the bridge, which it is 100 years. The mission is basically to exceed that 100-year service life. The composition of this team includes structural and post-tensioning engineering personnel, corrosion experts, maintenance engineers, as well as some contractors. The particular bridge, this bridge, is under maintenance asset management program. So one of the things that we always make sure is that our contractor is involved on all the decisions that we make for the bridge, as well as whenever a construction repair project is put out, that they get involved and they know everything that is going. When we ask them to do some repairs to the bridge, we would like for them to be aware of what the reasoning for it, and at the same time, which is very important, is to get their input, because believe it or not, we feel that our contractors, they do have a very good, they are very dedicated to the bridge, and they have a lot of knowledge that they can bring in. We also have academia consultants that we don't have, they are not permanent parts of the team, but whenever we have a need and we need to get some consultation, we give them a ring, we get them involved, and they always participate and share their opinions with us. To make the story short, we have evaluated the bridge for several years, and there is a consensus that due to the aggressiveness of the particular environment where this bridge is located, corrosion is considered to be the item of concern regarding the 100-year-plus service life that we are expecting. So, having said that, there is a lot of effort dedicated to corrosion control as well as to corrosion prevention whenever we can. We will have to say that this bridge, even for the time that it was built, between 1984 to 1987, most of the materials that they used were very good, and they are still used at this time. For example, it was one of the first bridges in Florida that used what we consider today high-performance concrete. It has performed very well. It has been holding the chlorides out for many years, and we do monitor that because we want to know exactly how the bridge and all its components are behaving. However, every now and then we can see, okay, we might have some problems in this area. This other area also will give us some problems. So basically what we do as a team is we analyze the potential problems, and then we prioritize the repairs. In this particular case, what we're going to talk here mostly today is on cathodic protection efforts on two areas of the bridge. One of them, the photo on the left-hand side, were for the, we call it the pylon footers for the main piers. These are massive, if I can see my right light, here we go. These are massive footers that extend all the way. They are mounted supported on piles and extend below water to support these two columns. The other area that we are concentrating on is on the main span columns. Now, there were two different things, and I'm going to get in with you about why are we doing this, what was the problems, but on the main piers, pylons, on the footers, we completed installing a galvanic cathodic protection system to prevent corrosion. On the columns in here, we have a different situation, and what we did was we installed an impressed current cathodic protection system. And let's talk first about the pylon footers. These are massive structures to support these two columns. This is the footing here, but it's supported by this column, and the inside of the footers is hollow. We do have access to it, but it's hollow, and typically it is full of salt water. We did, the particular situation with these footers was during construction, some cracks developed on the walls of the footing. It was discussed and the decision was made to just fill the inside cavity, the inside chamber, with salt water. That way, two things were expected to happen. Basically, to balance the hydrostatic pressure, so we would not have a whole lot of salt water going through the cracks. And the other thing was, it was estimated that, well, if we fill the inside with salt water also, it will limit the amount of oxygen on the rebars, so that would slow down the corrosion process. Over the times, all these have been monitoring, and we did a more in-depth inspection. I believe it was in the year 2012, and basically we drained the inside, which, by the way, is drained every 2 years during the routine inspection. We drained the inside of the footers and took a look at the cracks as well as at the reinforcement. Basically, what we found was that there was already corrosion showing up on some of the rebars, but not all the rebars. Only the rebars that were intersected by those cracks. So wherever we had a crack, we found that we had corrosion being developed. So we knew that over time, if the water was penetrating, that was going to extend into the rebar. We were going to have some more advanced corrosion problems to deal with. So the decision was made to, okay, let's see if we can work this out now to prevent future corrosion and concrete deterioration. Basically, this is what we did. For this particular situation, we were very fortunate because it had already been decided that the inside chamber is full with water. So basically what we did was we installed some galvanic anodes inside the structure with sufficient capacity to provide cathodic protection to the entire chamber. Even though we do know that the only places where we had corrosion was on the bars that were intersected by the cracks. So this was not a remedial action because we needed to take action. This was a pure preservation effort. We do not have a corrosion problem yet. We just know that we will have it in the future. So let's take care of it now before the problem gets a little bit better. So Basically, what we did, we installed a number of zinc anodes around the perimeter, make connections to the steel, and routed all the wires to outside the structure so we can connect and disconnect the system from outside without having to access the chamber. Basically, on the left-hand side, this is a shot of our anodes assembly. We installed like 4 of these, 4 assemblies inside each of the footers, because like I said, it was 2 footers like that. It holds the 2 towers. And then all the wires were routed to this little junction box. That's where we have all the switches, and we can make all the connections to monitor and make sure that the cathodic protection is working. And not only that, from the measurement that we do, we can even detect the anode consumption, so we can predict when do we need to go back and replace those anodes. Not going to spend too much time on this slide here. Basically, we take some measurements, and from the measurements that we take, we can determine that those anodes are working perfectly. We're getting the polarization that we need to warranty that, to ensure us that we have cathodic protection. The second cathodic protection system that we installed on the bridge was basically because of the same reasons. These were on the main span columns. We found that we had some cracks, vertical cracks throughout the columns. And there have been some previous efforts to actually seal the cracks. We already know that, I know that we have epoxy coated rebar for some reason in Florida have never worked, have never hold corrosion. Now, we know that we have water getting into the rebars, so we try to seal them. Now, for some structural reasons, either movement of the columns or expansion of the concrete, the cracks keep reappearing, or even some of the cracks that have been sealed, the sealing material cracks. So we have water penetrating our concrete all the way to the rebars. So we knew that we needed to do something, because again, if it is not taking care of it now, we will have to take care of it later, and it's going to be more expensive if we need to correct this after we have a lot of concrete deterioration that goes along with the corrosion. And basically, this is what we did. We designed a cathodic protection system for the splash area and above. And basically, what we impressed current to it such that it stopped corrosion. It was a very simple, basically a cathodic protection jacket. We used a titanium mesh anode to provide the current, and we used a basalt bar for shrinkage control. And the contractor used a lightweight aluminum form to cast the concrete. This is the final product. It is basically a cathodic protection jacket for the systems. As you can see, this is different because we need to use a power supply to provide the electricity. So we run the wires all the way to the inside of the bridge, to one of the segments, and that's where we locate all our electronics. So with our electronics inside, we can monitor what is going on the cathodic protection system. We also have, for this system, we have telemetry installed, which, from the office, we know where the system is operating or not. For those of you that might be thinking about cathodic protection, it's not anything that is new. It's old. There is already standards, industry standards out there that tells you how to measure, how to monitor the system and determine if it is working or not. And for the ICCP system, this is the same thing. Not going to spend too much, but you can take your measurements and you can determine if your cathodic protection system is working or not. On this particular one, it's very easy. Like I said, we have telemetry. From the office, we know if it is working or not. To finish my presentation, I think that the two systems that we have installed on this bridge are working very good. It's giving us assurance that for those particular components on the bridge, corrosion will not be a problem in the future. Again, these are not the only preservation efforts that have been implemented on the bridge. We do have, we have been constantly sealing cracks. We have been using NDEs for inspection of the tendons. We put a lot of efforts on maintaining our all the coatings, all the coated sections in good shape. And basically, to conclude, we are sure that we are convinced that bridge preservation efforts are a cost saving in the long run. Implemented them now, and you can be sure that you will be saving money on the future, in the future. That's all that I have. I appreciate your attention. Any questions?
What is the ongoing maintenance of the cathodic protection systems?
Well, all depends. On the galvanic system, those are very low maintenance, and you really don't have to. What we do is every 2 years we inspect them. We see how they are working, and we can determine the condition of the anode. The impressed current system is a little bit more delicate on the monitoring part of it. And the reason for that is that with the impressed current systems, those we use electronics and a rectifier to supply the current. If we put if the current is not sufficient, it will not stop the corrosion. If we put too much current, then we can damage the system on that. So that's the reason for on the impressed current system, just to make it simpler for us. Normally, on those systems, we will visit them once a month to make sure that everything is working. But now we have telemetry on it that from the office, it's almost maintenance-free unless something happens. Yes, sir.
For the discrete anodes that you had in the footings, you had 100 pounds of zinc. How did you choose that weight, and how long do you expect that to last?
Very good question. Two things. Basically, each assembly is 100 pounds. We have 4 of them, so we have like 400 pounds zinc. So basically, what we initially we estimated, and we think that we're going to have a very low consumption for 2 reasons. One is we do not have a whole lot of corrosion going on. The other thing is that the reinforcement is insulated. It's wherever the reinforcement will be good, if there is any, will be insulated. It's epoxy coated rebar. So that particular area is not going to be covered. It's not going to be taking current to consume the anode. So what we are doing, and that's the reason why we ran the wires outside, so we can monitor the current that is being put out to the steel. Now, based on that amount of current, we know the consumption rate of zinc on amp per year, and we can determine how long they're going to last.
Question about the impressed current system. Did you split it into different zones because some of it's closer to the water and in and out from time to time, and the other part is obviously higher up, so you have more uniform current distribution?
Indeed. And I think that I skipped mentioning that, but it was on my slide. I skipped talking to that, but indeed, you are absolutely correct. We broke it into zones such that we can manage how much current goes to the bottom portion versus upper portion.
I think I was going to ask about how you verified everything was electrically connected. I know that's a big deal and it's tough with epoxy-coated rebar.
It is. On epoxy-coated rebar, when the construction is done properly and the epoxy is good, we do have a lot of electrical insulation between the bars. In this particular case, what we have been done, and we have been doing on all the components, like I said, we do a lot of advanced investigations, so we know the percent of continuous bars on the columns, on the approach columns. We just finished, Matt Duncan is with me here. He's the engineer that basically handles all that from our office. I believe that we finished doing the footers and the columns on the threshold section probably a couple of months ago. A couple of months ago. So we stay ahead of the game. We know how much work will it be, but still, as part of the installation, we specify that they have to provide the electrical continuity. They have to measure and provide electrical continuity to all those bars that are not electrically continuous. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.